So hi everyone. So I'm going to make the link today between modeling and monitoring using sparse seismic. So let's dive right into it. So first, we will speak about uncertainties in CCS. This is something that is unavoidable, and I have something to propose to you to reduce uncertainties on a CCS project. We will see how we can do that using a synthetic CO2 injection example, and I will finish with two results. First, how we can reduce uncertainties during injection, and second, how we can show the potential of monitoring before injection to support permitting application. So, CCS uncertainties. So at the beginning of a project, in CCS, a lot of things, well, if not everything, relies on the model. And the model is used by many stakeholders, by operators, regulators, investors, to take decisions, secure permit, and move forward with the project. But when we are making this decision, we are still at the beginning of the project. So the model is still uncertain. We know that the model is still an approximation. So the question is, do we accept that uncertainty, or can we actively reduce uncertainties on this model? So let's go back to the basics. Modeling. When reservoir engineers, I'm a geophysicist by the way, when reservoir engineers most likely build a model, they come from multiple simulations. And at the end, they come to a P50, a P10, a P90 kind of model, and this is the approximation we will deal with on this CCS project. Now, what I want to do here is to go the reverse way. What if we could go back to the many CCS models that we have here on the CO2 injection and actually monitor to reach convergence, to find the model that is the closest to what's happening in reality, within the subsurface. So to show you how we could do that, we've built a synthetic use case in partnership with CMG, the Computing Modeling Group, and Spotlight. This synthetic use case is inspired from Northern Lights, actually, Utsira Formation. And it's an example with 5 injection wells over 10 years of injection, and it's a saline aquifer. We assume that we have a few information on this field, and we derive several models out of some variation in the petrophysical domain. So thanks to this slight variation in porosity, permeability, and so on, we reach an ensemble model of 120 models. And here we could see that as a Monte Carlo kind of representation of subsurface uncertainty. And we want to keep it that way. So let's take a look at the results of these models. You can see on the left side of the slide the end of injection. So it's a map of the CO2 plume, and you can see that the extent of the CO2 plume is quite different from one model to another. In this example, the top reservoir, the base reservoir, was not changed, so it's quite similar, and it could be even better than that in the modeling side. But this is a synthetic example. And in the end, this is the kind of CO2 extension that we have for the 91 models that CMG shared with us. You can see that, at the end of the 10 years of injection, we have a surface, map view of the reservoir that is affected by CO2, varying between 12 kilometers square to 48 kilometers square. So you have a variation of a factor 4 between the smaller CO2 plume extent and the bigger one. So let's see how we can reduce this scope of uncertainties that you can see on the right side of the slide. To do that, we will use the sparse seismic methodology that is called the focused seismic solution. So I will just remind quickly what is the focused seismic. It's a lightweight active monitoring solution, and the key idea is that we are not trying to build an image of the subsurface. We are monitoring specific location in the reservoir by using a few sources and receivers at the surface. Now, how can we locate these red spots that you can see on the map and on the section view? So we are using what we call the predictive monitoring. So to know where to locate containment and conformance spots, we are using the risk assessment study for the containment when you have abandoned wells and when you have leaks, potential leaks. And we are using the output of the model to know where to locate the conformance spot and when we should monitor the CO2 plume extent. But in this case, we've been using mostly the P50 scenario. So now we want to use them all. Quick view. These are all of the models from the synthetic use case. Well, not all of them, because we have 91 for 10 years and 1 per year. So, well, in the end, you have a map view of all of the CO2 plume shape, and it's just a lot of, it's just a lot of images. So I could synthesize this by saying, this is the kind of images that you have. You have a lot of dogs and cats, and you have some images that are similar to others. Based on this database, we want to apply a clustering algorithm so that we can see which CO2 plume looks similar. And we do that for the first year, the second year, and so on. And each time we see which CO2 plume are the most similar. At the beginning, some of them might just look the same. That's normal because we are just at the first year of injection. How can we actually build this cluster? With the spot seismic, the focus seismic, we specifically target and pinpoint specific location in the reservoir, and with the same amount of spot, we know the seismic response we expect. So here you can see on the left side one cluster spot detection signature, and on the right side a second cluster. So you have the same spot location, but the CO2 detection that we expect will not be the same. On the left side, we want to detect CO2 on all of the 6 spots. On the right side, we should have CO2 only on 2 spots. So just a few spots on the field, and we can already discard between models. So let's see, with the 91 models, the clustering we end up with. From 91 model, we do this clustering automatically, and we end up with 28 clusters and 28 spot locations for the first year of injection. You can see that we have the biggest cluster with 25 models in it, and then 15 models, and so on. Then, on the synthetic use case, we will simulate spot seismic acquisition. So we send the 28 spots, and CMG will tell us which spot saw the CO2. We come from a 10% detectability threshold, which is quite a conservative threshold to use in a saline aquifer, but that depends on the field. In this case, with the spot seismic detection at year 1, we detect CO2, and we can verify the cluster made of 9 models. And then you can do the clustering again on year 2, year 3, and so on until you reach convergence. The idea here, is to see how fast we can reach this convergence. So in this example, we converge towards the correct plume scenario in just 3 years. So that's how we can help reduce uncertainties while injecting on the field. If we just take the image from the beginning, you had an uncertainty between 12 and 48 kilometers square. Well, at year 3, so 7 years before the end of injection, you know already that the extent of the CO2 plume will be about 18 kilometers square. But that's for one model. So let's see what we could do pre-injection, how we could use this ensemble model to support the permitting process. We've done that by assuming that one model was representing most accurately the subsurface behavior. Let's do that for all models. Before injecting, it is assumed that any model could be true. So here we simulate the convergence across all cases. It's all of the gray curves that you can see on the left side of the slide, and you can see that on average, the convergence happens in about 4 years. Well, and importantly, we can also identify critical timing. Let's see here, you can see, let's say, the lifetime duration of each model. So you can see that the biggest CO2 clump shape is led by the 48 kilometers square at the top, and the lifetime of this model is approximately 3 years. So in 3 years, you will know if this model is really happening on your field. So that's how, if you have a threshold, if you have a maximal extent that you don't want to reach, then you can build the monitoring plan in order to answer the specific questions that you have and the specific risks that you have on the field. So here we know that most models will actually be discarded at year 3. And this also translates into economics. Well, in this case, uncertainty represents about $70 million of exposure in the case of the 45Q in the US. And you can optimize also injection to maximize the revenue on the field. So, to end this presentation, here clearly we have a few way forward. Of course, this is a synthetic example. It's not perfect. It's not really complex. It could be more complex than that. But the advantage is that all of the things that we are doing here is fully automated, and we could do it on any kind of ensemble model. And of course, at each occurrence, we should be able to model new model, actually. And yes, to increase the number of models as we go through the injection process. So to summarize, uncertainty is unavoidable, but it can be quantified. And we should model all scenarios, well, even the riskier, well, even the one that leaks, because that's specifically the one we want to monitor and we want to avoid. Focus monitoring can help accelerate model convergence, and the value with sparse seismic like this one, well, is created before injection and during injection. Thank you very much for your attention.
Thank you.